Good morning, everyone. Welcome back. Thank you for joining us. I'm Steve.
And I'm Scott.
And together we're Backyard Musings in the Backyard, Apple Valley, People's Republic of California.
Seems like a long time. Today we're talking about a topic that is
Interesting
and fairly common in the state of California.
But I didn't know the underlying thing. I didn't know this. This is fascinating to learn this.
Yeah.
Most earthquake energy turns into heat rather than ground shaking, sometimes hot enough to melt rock in microseconds. MIT's lab quakes reveal this hidden balance and its role in seismic risk. Would you like to know more?
When an earthquake strikes, the violent shaking that people feel represents only a small part of the total energy released.
That's a shocker. I thought that was it.
Yeah, just on the surface, right?
Yeah.
Quakes also unleash bursts of heat and trigger cascading fractures in the rock deep underground.
That makes sense. The fractures in the ground.
Determining exactly how much energy goes into each of these processes is extremely challenging to measure in the real world. Obviously, we can't see down there, right?
Right. To tackle this, MIT geologists studied lab quakes, a small-scale versions of natural earthquakes that can be carefully set off under controlled laboratory conditions. For the first time, they were able to calculate the full energy budget of these events, identifying how much is devoted to heat, shaking, and rock fracturing.
The researchers discovered that just 10% of a lab quake's energy produces actual shaking, while less than 1% is used to break apart rock and create new surfaces. The vast majority, averaging around 80%, is converted into heat near the epicenter. In some cases, the heat rise was so extreme that it briefly melted the surrounding material, turning it into liquid before cooling again. So we see that around. I mean, we have volcanic cinder cones all around. You may not notice them,
especially on the Eastern Sierras.
Yeah. And
those are fascinating.
Yeah, that whole valley, the Owens Valley, was just one big volcanic and tectonic experiment. I mean, it was just all kinds of stuff, and you can see it everywhere. So
what you're seeing now, we put up a graphic. This is what MIT shared. I guess why I thought this was fascinating. It looks like a cylinder that we in the construction industry break, a core that we break to find out the strength of the concrete. And this is how they figured out what, I don't know if they compressed it or they just shook it, but this is showed
both.
up. Yeah.
You'll do more than one core, right?
I'm sure. I'm sure. Well, and on the job site, it's 3 per pour, or 3 per truck. Sometimes it could be 3 per truck.
Oh, okay.
Each truck is 10 yards.
Make sure they're not getting over on you.
Well, make sure that there's proper air entrainment, there's proper admixtures, it's a slump, all that, Okay. All right. They also showed that this balance of energy is not fixed, but depends on a region's deformation history or the event to which its rocks have been altered by past tectonic movement. That makes sense. I mean, when you have fracturing, it's going to be different the next time and the next time.
Or a continuation. Right?
Yeah. That history influences how much of the quake's energy goes into heat, motion, or fracturing.
Quote, the deformation history, essentially what the rock remembers, really influences how destructive an earthquake could be, says Daniel Ortega Arroyo, a graduate student in MIT's Department of Earth, Atmospheric, and Planetary Sciences. Going on with a quote, that history affects a lot of the material properties in the rock, and it dictates to some degree how it's going to slip.
The team's lab quakes are a simplified analog of what occurs during a natural earthquake. Down the road, their results could help seismologists predict the likelihood of earthquakes in regions that are prone to seismic events. For instance, if scientists have an idea of how much shaking a quake generated in the past, they might be able to estimate the degree to which the quake's energy also affected rocks deep underground by melting or breaking them apart. This in turn could reveal how much more or less vulnerable the region is to future quakes. Makes sense.
And that, like our area, right?
Yeah.
We talked about San Andreas Fault. I mean, we're 30
Alaska,
miles, or less than 30 miles from
Greece. We're going to study something this afternoon on Greece. Yeah.
Another quote, we could never reproduce the complexity of the Earth, so we have to isolate the physics of what is happening in these lab quakes, says.
Let me do this. This is Czech.
Okay.
Maciej Pech.
Okay. Thank you. Associate Professor of Geophysics at MIT. Going on with the quote, we hope to understand these processes and try to extrapolate them to nature. So copyright.
Yep. Here's the citations. Petch and Ortega Arroyo reported the results on August 28th in the journal AGU Advances. Their MIT co-authors are Hogi Ogafari, now I'm making that up, Hogi, and Camila Catania, along with Zheng Gong and Roger Fu at Harvard University, and Marcus
We're not
Ol.
making this stuff up.
And Marcus Ol and Oliver Plumper at Utrecht University in the Netherlands. Plumper.
Okay. Earthquakes are driven by energy that is stored up in rocks over millions of years. As tectonic plates slowly grind against each other, stress accumulates through the crust. When rocks are pushed past their material strength, they can suddenly slip along a narrow zone, creating a geological fault. As rocks slip on either side of the fault, they produce seismic waves that ripple outward and upward. That's where you get the shaking. So
Yeah.
right.
We perceive an earthquake's energy mainly in the form of ground shaking. That's what we can see and feel, which can be measured using seismometers and other ground-based instruments. But the other two major forms of the quake's energy, heat and underground fracturing, are largely inaccessible with current technologies, unless you're a mole.
Yeah, but I mean, we've talked about it before. Sometimes we see a rolling
on
the surface. Sometimes it's just a
jarring. Yeah.
Sometimes it's
it's different
constant
kinds.
shake.
Yeah. And then the earth might split. We've seen that on the highways and stuff.
We've had that.
Do that. If you drive in Fairbanks to Anchorage, you'll see the road. It's they've got patches, where it's fractured apart, big time. And going down Walu, you can feel that da-thum. It's like rhythmic every so often.
Interstate 15 through the Cone Pass, same thing.
Yeah.
Another quote: unlike the weather, where we can see daily patterns and measure a number of pertinent variables, it's very hard to do that very deep in the earth, Ortega Arroyo says. Going on with the quote, we don't know what's happening to the rockets themselves and the timescales over which earthquakes repeat within a fault zone on the century to millennium timescales, making any sort of actionable forecast challenging. So,
to say the least.
Yeah, so they got to have these little model things that they put together. So,
to get an idea of how an earthquake's energy is partitioned and how that energy budget might affect the region's seismic risk, he and Petch went into the lab. Over the last 7 years, Mathieu Petch's group at MIT has developed methods and instrumentation to simulate seismic events at the microscale in an effort to understand how earthquakes at the macro scale may play out.
Another quote, we are focusing on what's happening on a really small scale where we can control many aspects of failure and try to understand it before we can do any scaling to nature, Ortega Arroyo says.
For their new study, the team generated miniature lab quakes that simulated a seismic slipping of rocks along a fault zone. They worked with small samples of granite, which are representative rocks in the seismogenic layer, the geologic region in the continental crust where earthquakes typically originate. They ground up the granite into a fine powder. I'd like to see that. That's pretty cool.
You got some in your front yard.
And mixed the crushed granite with a much finer powder of magnetic particles, which they used as a sort of internal temperature gauge. A particle's magnetic field strength will change in response to a fluctuation in the temperature. All right, we're going to take this slide off so that you can see our chiclets here.
The researchers placed samples of the powdered granite, each about 10 square millimeters and 1 millimeter thin, so that's pretty thin, right?
Yeah.
Between two small pistons and wrapped the ensemble in a gold jacket.
Oh, gold. Gold's in the earth. 99% of gold on the earth is in the earth.
Okay. Then they applied a strong magnetic field to orient the powder's magnetic particles in the same initial direction and to the same field strength. They reasoned that any change in the particle's orientation and field strength afterward should be a sign of how much heat that region experienced as a result of any seismic event.
That makes sense. I'm glad they broke that down. Once samples were prepared, the team placed them one at a time into a custom-built apparatus that the researchers tuned to apply steadily increasing pressure, similar to, just like the core samples. Pressures that rocks experience in the Earth's seismogenic layer, about 10 to 20 kilometers below the surface. They use custom-made piezoelectric sensors developed by co-author Ogafari. That's Hogiokafari, which they attach to either end of a sample to measure
You
any.
remember that?
I remember that. It's this nonsense that I remember, you know. It's all up in here. To measure any shaking that occurred as they increased the stress on the sample.
They observed that at certain stresses, some samples slipped, producing a microscale seismic event similar to an earthquake. By analyzing the magnetic particles in the samples after the fact, they obtained an estimate of how much each sample was temporarily heated, a method developed in collaboration with Roger Fu's lab at Harvard University. They also estimated the amount of shaking each sample experienced using measurements from the piezoelectric sensor and numerical models. The researchers also examined each sample under the microscope at different magnifications to assess how the size of the granite grains changed, whether and how many grains broke into smaller pieces, for instance.
Okay, so they dissected this. Eventually, they're going to have to do one where they do the pressure and then they let it set for a week or a month, and then do the pressure again. So, you know, over time, you know, over centuries and millennia.
I would think that they would have to go to a larger model to do that, right? Because
Maybe.
1 millimeter thick, that's pretty brittle, right?
Yeah, it is
so
brittle.
They're going to have to increase that a little bit, like a layer of dirt or what do they call that?
A film.
No, it's like the layers in the
strata.
In the earth.
Strata.
What do they call that?
Strata.
No. It's like the layers, the different layers. There's like a layer. You'll be driving along with a carved away from a freeway.
Yeah.
And you'll see a layer, and then there'll be a totally different layer above that, and then another layer above that. I forget what they call it, but anyway, my dad's rolling over his grave because I can't remember that. So,
from all these measurements, the team was able to estimate each lab quake's energy budget. On average, they found that about 80% of a quake's energy goes into heat, while 10% generates shaking, and less than 1% goes into rock fracturing or creating new, smaller particle surfaces.
Another quote here. In some instances, we saw that close to the fault, the sample went from room temperature to 1,200 degrees Celsius, which is pretty high.
That's hot.
Yeah, in a matter of microseconds, and then immediately cooled down. Cooled down once the motion stopped. That's according to Ortega Arroyo. Going on with the quote, and in one sample, we saw that the fault moved by about 100 microns, which implies slip velocities essentially about 10 meters per second. That's a lot.
That's a lot. Yeah,
that's about 30 yards, right? A little over 30 yards
per second.
That's a lot. It moves very fast, though it doesn't last very long.
And that's what earthquakes are about.
Well, we hope.
Yeah.
We hope they don't last very long. At least that's the thing I always think about. You know, whenever you feel it, you're thinking, okay, that wasn't so bad. Where was the epicenter? And maybe that was the epicenter, but most of the time it's farther away, and they're the ones that really get the brunt of it. So I can think of many quakes that have been like that.
I'm just going to throw this out there just as a hypothesis. You know, in the end times, the earth will roll like a scroll, right? That's indicative of, you know, Armageddon when the Savior comes. That's indicative of like earthquakes, right? Scroll. This heat that they're talking about, that's probably how everything like at the bottom of the ocean, the trash and the stuff, that's probably how it's going to get vaporized so that there's no trace in those, you know, when we move into the celestial.
You think just the trash is going to get vaporized?
Well, the ships that have sunk in the sea, and what I'm talking about is the random stuff that humans have left behind, you know, that's all going to get vaporized and melted back into the earth. Okay. This is basically from what we're studying here. That's my hypothesis.
You heard it here.
Here you go. The researchers suspect that similar processes play out in actual kilometer-scale quakes. Quote, our experiments offer an integrated approach that provides one of the most complete views of the physics of earthquake-like ruptures in rocks to date, Petch says, continuing the quote. This will provide clues on how to improve our current earthquake models and natural hazard mitigation.
Okay, wow. So not just shaking. Not just shake,
but
rattle,
stirred,
and roll.
But stirred
and heat and
I never knew
separation. This. And yeah, it's the whole package.
Hats off to the MIT folks, right?
Yep. We're grateful for those guys that are so smart.
Impressive.
They give us headaches.
And it was a Czech guy from Czech Republic.
Well, there's a lot of those guys.
Oh yeah.
Who's that guy? Who's Hoagie? Where do you think Hoagie was from?
He's probably like Hungarian or something like that. Ogafari, maybe he's Irish. Ghaffari is probably, what do I want to to say
Middle Eastern
Middle
Irish?
Eastern, like Tripoli. What's that country where Tripoli is? So it's Libya.
Oh.
So he's probably Irish Libyan.
Oh, okay. Well, if you know, let us know.
All right, folks. Thanks for joining us.
Take care, everyone.
We'll
Thanks.
see ya.